You've already learned about the basics of ionic bonding. Today we're going to talk about some pictures, or the basics of some pictures that we can draw to help us represent those ionic bonds. That will help us figure out which atoms will bond together and how many of each kind of atom we need. The pictures that we draw to help us decide which atoms are going to bond and how many of them will bond are called Lewis electron dot structures. It's just a visual representation or a picture of the valence electrons of an atom. So we need to remember from last semester how to find valence electrons based on the electron configuration or based on where that element is on the periodic table. These pictures are based on the idea that all atoms want to achieve a stable octet. Again, this is something we talked about last semester. Most atoms in compounds tend to have the electron configuration of a noble gas. A noble gas has a full s orbital and a full p orbital in its last energy level. That means it has 8 valence electrons. So, thus the octet rule. Atoms that are stable have 8 valence electrons. Atoms that don't already have 8 valence electrons will either lose or gain to make that happen. So let's start with just the basic elements. Notice we've skipped the transition metals in this picture, and we also only went 4 rows down. Let's start with the first column on the left. How many valence electrons does hydrogen have? Hopefully you just said 1. Hydrogen only has 1 electron. So we draw a dot to represent an electron. Remember from last semester that everything in that same column also has that same number of valence electrons. You could figure this out with the electron configuration if you need to. Usually it's easier just to memorize that everything in that column has 1 valence electron. So the dot structures for the rest of those elements, lithium, sodium, and potassium, all look the same. Now you might be wondering, why did I choose to put the electron here? Why not on the other side? Truth is, it really doesn't matter. You could move these electrons around the symbols for the elements more or less anywhere that you need to put them. We usually pretend that there's like a little square around the element. So we usually draw electrons on 4 sides, but again, you can kind of move them wherever you need to move them. Let's go on to the next column. How many valence electrons does beryllium have? Hopefully you know that's 2. Notice on this picture that I drew them on opposite sides. They don't necessarily have to be on opposite sides, but they should be on different sides. So you could have drawn one here and one on the top, or one here and one on the bottom, and so forth. But the electrons should be on opposite sides for that picture, or at least on different sides. Again, same column, magnesium and calcium are going to look the same. Next column, boron, has 3. Again, it doesn't matter what sides they are on as long as they are on different sides. Aluminum and gallium will be the same. Next column is carbon, and that has 4. And here is where you can start to see that we pretend that there's a square around the symbol because there's 1 electron on each side of that square. Silicon and germanium would be the same. And now if you think about that square kind of idea, and we go to the next column, how many valence electrons does nitrogen have? Well, if you follow the pattern, 1, 2, 3, 4, nitrogen should have 5. But if we're pretending that there's a square and we only have 4 sides to work with, we have 5 electrons to put on 4 sides. That means we're going to have 2 electrons now on the same side. So we have 1 pair and 3 singles. Just like before, it doesn't really matter what side you put the pair on. You just need to have a pair and 3 singles. Phosphorus and arsenic would look the same. Oxygen now is going to have 6. Hopefully you'd be able to predict that that would be 2 pairs and 2 singles. You can choose whatever sides you like for the pairs and the singles. Sulfur and selenium would be the same. Fluorine would have 7 valence electrons total, so that's 3 pairs and 1 single, whatever sides you like. Chlorine and bromine are the same. Now this last column is going to be a little bit different. Helium, we know, has how many electrons? 2. So we draw 2 electrons for helium, and we pair them together. And the reason we do that is to differentiate helium from beryllium. Helium is a noble gas, so even though it doesn't have a stable octet because it only has 2 electrons, it's still pretty happy the way it is. So we put its electrons together in a pair already to make it look different from beryllium and magnesium and the rest of that column. Once you get past helium, then the rest of the noble gases follow suit as you expect they will. So fluorine had 7, neon is going to have 8, that's 4 pairs. Argon and krypton are the same. If we're going to talk about ionic bonding though, we also have to talk about ions. And so you can take those dot structures, the very same pictures that we were just drawing, and you can also represent ions with those pictures. So we can talk about cations and anions and what those dot structures would look like. Remember that a cation is one that has a positive charge. It's positive because it's lost an electron, and this usually happens with metals. Metallic elements make cations. What would the dot structure look like? Well, it depends on what you start with. If you started with sodium, which has 1 electron to begin with, and then sodium loses that electron, you don't have any electrons left in your picture over here. Instead, we have a plus sign. That's to symbolize that the sodium ion is now positive. It's positive because this electron came off. Magnesium is going to lose 2 electrons. Again, there's no electrons left in the picture. Instead, we have a 2 plus or a plus 2. You can switch the order of these two things in this class, that's okay. And the 2 separate electrons that have been lost. Aluminum is going to lose 3 electrons, plus 3 or 3 plus, and 3 separate electrons that have come off. One note about the transition metals. Transition metals may form multiple ions. What that means is that they can choose how many electrons they want to lose more or less. For example, iron sometimes loses 2 and sometimes loses 3. And that just depends on what it's bonding with or reacting with, what the surroundings are, what the situation is. I don't expect you to know whether it's going to lose 2 or lose 3. Just know that it can lose a different amount of electrons. So there's not one set amount that it has to lose. Okay, let's talk about anions. Anions are those that are negatively charged. That's because they have gained an electron, and this usually happens with nonmetals. So here's an example of a dot structure. We started with chlorine, which has 7 electrons. Chlorine would rather gain 1 than try to lose a lot, so it's going to gain an electron. That means we add a dot to our picture, so chlorine now has 8, 2, 4, 6, 8, and because we have an extra electron, we have an extra negative, so we put that little negative off to the side. Here's another one. Sulfur. It would be easier to gain 2 rather than lose 6. So sulfur ends up with 2 extra dots. That gives it a full octet. And we put a -2 or a 2 minus off to the side. That shows that there's 2 extra electrons now. And phosphorus would follow suit, except phosphorus gains 3. Okay, let's talk about some common ions that we can use to make ionic bonds. Many of the ions that we will deal with in ionic bonding are called monatomic. That means there's 1 atom involved. Like a monotone voice would be speaking in 1 tone of voice, or when you listen to speakers in mono versus stereo, that's 1 speaker versus 2. So monatomic means 1 atom. The first kind of monatomic ions are the ones that only have 1 possible charge. There's a set number of electrons that they lose or gain, and that's just what they do every time. These are those ions that we've been using as examples for a while. For example, most of the things in column 1, column 2, there's aluminum, nitrogen, phosphorus. Notice we skipped the entire carbon family. We'll talk about why a little bit later. We've got a few out of the oxygen family and most of them out of the halogens. Notice again, the metallic elements are the ones that lose electrons. The non-metallic elements are the ones that gain electrons. If we're going to be doing lots of ionic bonding, we also need to know what to call these ions. And oftentimes we need to know that so that we can differentiate the ion from the original atom. The two things are different. One has either lost or gained electrons, and that makes it kind of a different entity than what it started as. So we need to know ion names. Cations are pretty easy. You name the element, for example, calcium, and then you add the word ion. So Ca+2 is the calcium ion. Not too difficult. Anions are a little bit different. For an anion, you're going to take off the ending of the element name and replace it with IDE. So things like nitride, phosphide, oxide, sulfide, and fluoride. And once we've worked with these a while, you'll get a pretty good feel for how much of that element's name to take off and then how much of it to leave. As we first start working with these, if you don't take off the right amount, that's okay as long as you have the IDE at the end. So if you put phosphoride instead of phosphide, that's okay. Okay, the second kind of monatomic ions are the ones that can have more than one common charge. These are only cations, and it's mostly the transition metals. We talked about that already, like iron, which could lose 2 electrons or it could lose 3. There are a couple of exceptions. Tin and lead can also have more than one possible charge, and they are not in the transition metal block. So you'll probably just have to memorize those two. Transition metals and lead and tin can have more than one possible charge. One side note, when you have an ion that has more than one possible charge, when we get to naming, we're going to need a way to write down or communicate which charge it used in that particular compound. The system that we use is called the stock system for naming ions. It's really pretty simple once you get used to it. I know this is a lot of information on one slide. I don't expect you to memorize this information. For example, if we take copper, copper has 2 possible charges that are pretty common, +1 or +2. The stock name, or the system that we will use to differentiate between this one and this one, takes whatever that charge is and uses a Roman numeral to represent that charge. So copper 1 versus copper 2. Pretty simple. Take the charge, make it a Roman numeral. You really only need to know your Roman numerals about up through 6 or so. The reason I put these last 2 things on here is that I think it's kind of interesting so that you can see, for example, where does the symbol for copper come from? It's Cu instead of Co. It comes from the Latin name. So the Latin root, or the base, for the name of copper is Cupr. And then the old system used to have a different suffix or a different ending depending on what charge it was. The lower charge had OUS, the higher charge had IC. Sometimes you still see that on chemical bottles, especially the older ones that we have in our chemical closet. So if you see cuprous or cupric, then that's just telling you one of those is the lower charge, one of those is the higher charge. Iron works the same way. Iron is either +2 or +3 most times. So the stock name would be iron 2 or iron 3. Here again, you can see where the symbol comes from. It comes from the Latin name, which would be ferrous or ferric, depending on what the charges are. Lead is either +2 or +4, so lead 2 or lead 4. And here's where its symbol comes from, plumbous or plumbic. Tin, +2 or +4, tin 2, tin 4. Stannous or stannic. And then mercury's a little bit different. Mercury has a couple of different ions. One of them is Hg2 plus 2, which is a little weird, and its name is dimercury 1. And then the other one is much simpler, Hg plus 2, mercury 2. Again, I don't expect you to memorize the stuff off this page. I'm just using these as examples to show you there are ions that have more than one possible charge. When we get to naming, we're going to have to deal with communicating what that charge is. Okay, moving on, almost done. In addition to monatomic ions, there are also ions that are polyatomic. So just like a polygon has multiple sides, a polyatomic ion has more than one atom. So it's a group of atoms that are bonded together, and as a group, they have a charge. There are several of these. I don't expect you to memorize them. There is a chart on the back of your periodic table on your notes packet that lists the different polyatomic ions. Polyatomic ions act as one unit in an ionic bond, so you'll treat them as a single item, even though there's more than one atom involved, because they have a charge as a group. So as that group, they have a single charge. If you take a look at the chart on the back of your periodic table, the one warning that I usually give to students is that there are a lot of these polyatomic ions that look very similar and sound very similar. So double check. Be careful that you're reading the right one off the list. Okay, that should be it for dot structures.